Today's lesson is a continuation of section 4.5, graphing using slope-intercept form. We just recently learned a third method now to graph. We knew two methods before. This is our third one, so now we know all three of the methods that we're going to talk about when it comes to graphing a linear equation this year. Here are the three methods just as a reminder. We know how to use ordered pairs method where we plug in 0, 1, and 2 in for x and for the equation, find three ordered pairs, plot those points, and graph and make our graph. Method number 2, we use the x and y intercepts. We plug 0 in for x, 0 in for y in the equation, and that'll give us our x and y intercepts, those 2 points that we can use to graph the line. And now the third method, graphing using slope-intercept form. Again, what does slope-intercept form look like? Well, here it is right here, y equals mx plus b. It looks familiar to us. It's something we've been using when we use the first method, the graph ordered pairs method. I've always felt the easiest way to use that method is if you have the equation in this form already. And so getting the equation into this form won't be that won't be a new thing for us in this lesson. If the equation's already in this form, then the nice thing about slope-intercept form is the two things you can pick off very easily are the slope and the y-intercept. When you just look at the equation, you don't have to do any other kind of work. The numbers are just right in there. For example, this first problem here. So problem number 1, it's got y equals, and then everything else is on the other side of the equal sign. So this means it's in slope-intercept form. It's solved for y. When the equation's in slope-intercept form, I can just say, here's the slope and here's the y-intercept. Again, that's why it's named so. I can just find those two things very easily if it's in this form. The slope is the coefficient of x. Or again, as I say sometimes in class, the number that's right in front of x. In this case, it's -4. And for this one, the y-intercept to be -10. Remember that sign in front of the 10 is subtraction. So I have to think of it like -10 when I pick out the y-intercept. Problem number 2 here, same kind of thing. It's in slope-intercept form already, which is nice. So I just got to pick off the key information, as I call it. And then we could go ahead and graph if we're supposed to graph these problems. The slope for this one, even if it's a fraction, that's okay. -7 over 2, or -2/7, or sorry, -2 over 7, or 2/7 for my slope. And my y-intercept, it can be a fraction too, that's all right. B can be 1/2 for that problem. If the equation's not in slope-intercept form, we talked a little bit about this in the previous lesson. If the equation's not in slope-intercept form, that's all right too. I can just change it around. We've had practice doing this as well. We know how to solve an equation. We know how to kind of manipulate it and move numbers around. Well, so this should be not entirely new to us as well. If I want to get y by itself here in problem number 3 and solve this equation for slope-intercept form, it says -15. So the first thing I'm going to do is I'm going to add 15 to both sides. That'll get rid of it from the left side here. It cancels out. All that's left now is the 5y on the left side. And on the right side, I have 3x plus 15. I can't combine those because they're not like terms, but I can just write it like that, 3x plus 15. So now I have 5y. To get rid of the 5 from the left side, I just got to divide every single thing in the equation by 5. The 5's cancel out. I get y equals. And over here, I'll get 15 divided by 5 gives me 3. How do I deal with this little part right here? Well, as I've told students in class 2, and we've started to kind of learn, when we're dealing with slopes, we often see it as a fraction or as a ratio, like rise over run. So when you divide 3 by 5, you actually shouldn't change it into a decimal in these kind of cases. It's easier, especially if I'm going to graph it, to just leave it as this fraction. 3 divided by 5. That's what I'm trying to do, is take 3 divided by 5. Well, that's what that fraction means, so I'm just going to put 3 over 5 and then keep the x with it. If I was picking out the slope and y-intercept of this one, then I'd say the slope is 3/5, and the y-intercept is 3. Sorry, I divided by 5, but I got 3 for an answer. So that's what it looks like. Kind of either getting an equation in slope-intercept form, and then also just picking off the key information. We worked on this. This is kind of a little bit of a review of the previous lesson, so students should kind of know how to do this already. When it comes to graphing using this form, what do? Well, again, we talked about this in the previous lesson. If you're still having trouble with it or need a little refresher, then look back to the previous lesson on section 4.5. That one also shows you how to graph using slope-intercept form. But I will review it here as well. I'm also going to have if you're taking notes along with me, the things in red here are the things I'd like you to write down. This is kind of the process. We went through this last lesson, so we kind of saw it firsthand, and got to do this ourselves and experience it, so we could kind of figure it out, kinesthetically or working with it. But now here's, if this may make a little more sense now writing it down, and also if you have to look back in your notes all of a sudden and kind of review, well then here's something a couple lines that might be important for you. What do we do with these two pieces of information? Well, the y-intercept tells us where to start, tells us it's kind of like a starting point. The y-intercept tells us where the line goes through the y-axis. So that has to be one point that's on this particular line. I'll kind of demonstrate this with this example that I have up here. Y equals negative 4x plus 1. So again, if I'm going to pick off the key information, it's in slope-intercept form. So I can pick out the slope, which is negative 4. I can pick out the y-intercept, which is 1. And knowing just those two numbers, that's enough to make a graph of this equation. The y-intercept, again, is, as I say, it's kind of like a starting point. It tells us where this line crosses the y-axis. So if I know that the y-intercept right here is 1, then on the y-axis I can go up 1 and put a point right there, because no matter what this line looks like, if it's some kind of positive slope or some kind of negative slope or zero slope or any kind of slope at all, no matter what it looks like, it's going to go through this point for sure. I know that because the y-intercept is 1. So that's why I refer to it as kind of a starting point to get our graph going. I know the line goes through this point right here. That's the y-intercept. As I recommended, I think, in the previous lesson, what I have students do then usually is just cross off the y-intercept. After you've used it, it doesn't do us any more good. It's just kind of a good starting point, but if people don't cross it off, sometimes they start to confuse that or get it mixed up with the slope and start using it with the slope. We don't need that. So instead what I say is just cross it off, and now let's just concentrate on what the slope of the line is. The slope, as it says there in the second bullet point, the slope tells us the steepness of the line. It's a measure of steepness, as we talked about. So using that, we can find more points that are near the y-intercept. So this slope says negative 4, and again, I also think of slope as, you hear the popular phrase sometimes, rise over run. And that reminds us that we have to go up or down so much first, and then to the left or right. So in this case, if I think of rise over run, well, I'm going to make this into a fraction so that I can think of how much I go up or down and how much I go to the right. How do I make negative 4 a fraction? I just put that over 1. Any number I want to make into a fraction. If it's just an integer or a number by itself, I can just put that number over 1, and all of a sudden it is in fraction form. So the slope is negative 4 over 1, I could think of, and that means, well, negative 4 means go down the y in the y direction, so I'm going to go down 4 and to the right 1 to find my next point. So if I go down 4 from here, 1, 2, 3, 4, and then to the right 1, there's another point that should be on this line. 1, 2, 3, 4, over 1, there's another point that should be on this line. So that's how I can make the graph of this equation, is by using the y-intercept, finding that as a kind of a starting point, and then using the slope from there. Maybe just going through one more review here. This problem below says 4y equals 12x minus 16. Again, this equation right here, this one's not in slope-intercept form right now because it's not y by itself on the left side. It's not solved for y. So what I have to do is, to get y by itself, this says 4 times y. I do the opposite of what it's doing to the variable. So if it's multiplying, I divide everything by 4. It'll cancel out the 4's on the left side here, so I just have y by itself. 12 divided by 4 gives me 3x. 16 divided by 4 gives me 4. So now I have y equals 3x minus 4. Now it's in slope-intercept form. Now I can pick off the numbers for slope and y-intercept. My slope is 3. My y-intercept is negative 4 if I'm going to graph this one. The y-intercept tells me to go 1, 2, 3, 4 down 4 on the y-axis there, and again, then cross it off. Otherwise, students sometimes get mixed up, and then for the slope, they go like up 3 and over 4. They keep using the y-intercept, but that's not what we're going to do here. The y-intercept is just a nice starting point for us and tells us where the line goes to the y-axis. That's all we need it for. Then the slope is 3. Again, to think rise over 1, I can put 3 over 1, which will remind me go up 3 and then over 1 spot. Up 3 over 1 to the right. There's the graph of that equation. So again, just a little bit of review, but that's how we use this method to graph using slope-intercept form. I'm going to talk about one other new thing here in class today, and it's going to deal with something we're going to use a bunch of times the rest of the year here, and something that's important for the MCA standards and something they want us to know about, and it is something students have heard about before, but now we're going to make a few more connections with it. To do so, I'm going to talk about these two equations that I have shown right here. And I'm going to graph these two, and we'll see if we can notice some kind of similarity between them. That first one, y equals 3x minus 2, Again, like we've been doing, I can pick out the slope and the y-intercept. They're right there in the equation because the equation's solved for y. The y-intercept is -2, so that'll be a point right here on the y-axis. And then I'd go up 3 over 1, up 3 over 1. And so there's the graph of that particular equation, the blue one. Now I'm going to graph this red one as well. To solve it for y and get it in slope-intercept form, I got to divide everything by 2 first. So I'm going to get y equals, well, 3x plus 5. And if I graph this one, the y-intercept is 5. 1, 2, 3, 4, 5. The slope is 3. 1, 2, 3 over 1. 1, 2, 3 over 1. Something like this for my line. Oops, and I kind of missed. I'm going to try one more time because it is kind of important for this one that I do get it pretty correct. That looks a little better. So there's the graph of the red line. I'm going to ask students to see if they can compare these two equations. Did they notice anything similar about the two that they can even tell either from the equations or even just from looking at the graphs of them? And usually, as I kind of help out a little bit, students are able to notice that the lines go up at the same kind of angle, or notice that they are going up almost at the same kind of slope, or they can spot out that the slope of these two equations, what do you know, is the exact same. All this kind of leads to the fact of what type of lines we call these. These are actually called parallel lines, and it's something that students have heard in the past, but now we're going to again talk about it a little more in the upcoming sections here. Parallel lines, what do? They're lines that increase at the same slope as we're noticing right here, or you could say they have the same angle, or the exact book definition is parallel lines are two lines that in the same plane that never intersect. These lines will never get any closer to each other. They'll never cross at all. They just continue on and on forever in both directions and never touch each other. So I'll have the students write down the book definitions here. If you're taking notes along with me, go ahead and jot that down too in your notes. And also one thing I'm going to have you write with it too. Parallel lines are two lines in the same plane that do not intersect. And how we're going to see it more, how we're going to look for this to know that lines are parallel even without graphing, is that parallel lines also have the same slope. So that's something else we're going to notice as we're analyzing equations and looking at them and kind of telling things that we're kind of figuring out things about them as we graph them, or even before we graph them. We should be able to figure out certain information about them. Well, as we look at these two, again, here's kind of be a key thing to look at and analyze an equation with is by looking at the slopes. And if we notice that the slopes of these two lines, like I said, are the same. They both have a slope of 3. What do you know then? They're both going to increase at the same angle, and so they're going to be parallel lines. Going along with this, we'll have some problems where they might just ask us, the book or MCA problems or whatever we work with, might just ask us how can we tell whether the two lines are parallel or tell whether these lines, any of these lines are parallel that they have. And what I want us to be able to do is not even have to graph those equations. I want us to just be able to look at the equation and tell whether a line is parallel or not. So if I look at these, we'll call them the red, the green, and the blue. Well, red line, green line, and blue line. As I'm looking at those two equations, I want the students to be able to look at those and not even have to graph them. They can tell which lines are going to be parallel right now. If I look at them and kind of compare them to each other, well, I notice that this one has a slope of -2. M equals -2. This one has a slope of 2. And this last one has a slope of also -2. So if I'm gonna tell anything about either of these lines, I can tell that right here, the first line and the last line, the red and the blue one, those should be parallel lines when I graph them because they have the exact same measure for slope. They're both negative slopes, and in fact, they're both -2 for slope. I'm going to graph them here just to kind of show that. If I graph that first one, the y-intercept is 8. So I'm going to go up 8 on the y-axis, and then down 2 over 1. There's a point. Down 2 over 1. There's another point. There's the graph of the red line. I'll graph the green line here too just to kind of compare. 1, 2, 3, 4, 5. The y-intercept is +5 for this one. I'd go up 2 over 1, up 2 over 1. There's the graph of the green line. And the blue line, 1, 2, 3, 4, 5. The y-intercept is also +5. Down 2 over 1, down 2 over 1. There's the graph of the blue line. Again, my hand isn't perfectly steady, so you can kind of see here at the end they almost start to come together. But really, if I had drawn these lines perfectly with my hand here, they would be at the exact same slope, and we would notice. You can kind of see it, see it up in this area that I drew them pretty well. They're almost the exact same distance apart there as the lines go on. This is what parallel lines do. They never get any closer to each other. They always stay the same distance apart because they're, in this case, going at the same angle. They have the same slope. They both go down 2 points and over 1, down 2 points and over 1, down 2 points and over 1 to find more points on the line. So if they both have that same angle, well, it makes sense that they're always going to stay the same distance apart. Then they're never going. Neither the rates for them are changing, so they're always going to stay just the same distance apart as they go up and down the line. So these are parallel lines; they'll never intersect. What I want us to notice, though, is just by looking at the equations, I want our students to be able to tell that without even having to graph them.